Have you ever stopped to think about how your bank or your favorite social media app somehow keeps track of billions of little pieces of information without the whole thing just collapsing? Well, it all goes back to this brilliantly simple idea from the 1970s that literally brought order to the chaos of data. Today, we're diving into the relational model. Let's do it. Okay, so let's imagine you're running a university. You've got thousands of students. You're going to have students with the exact same name, right? People are moving all the time. Records are everywhere. How on earth do you make sure that Amit Sharma in computer science doesn't accidentally get the grades for Amit Sharma over in mechanical engineering? I mean, it sounds like a total nightmare of messy, duplicated, and just plain wrong data. Well, the answer to that nightmare is the relational model. Now, don't think of it as just a way to store data. It's so much more than that. It's a logical blueprint, a master plan for organizing information that guarantees every single piece of it is consistent, accurate, and most importantly, easy to find. It's the elegant solution that takes that data chaos and turns it into clean, structured order. So, how does this whole thing actually work? Well, it all starts with a really solid plan. You can't just start throwing data into the system. First, you have to define the structure, kind of like an architect who has to draw up a detailed blueprint before anyone can start building the house. The basic building block here is something called a relation. Now, that's a fancy academic word, but honestly, just think of it as a table. You know, like a spreadsheet. It's got columns, which we'll call attributes, and it's got rows, which we'll call tuples. But here's the kicker, the big difference. This isn't just any spreadsheet. It's like a super spreadsheet with very, very strict rules. So step one is defining that blueprint, and we call that the schema. This is where we decide upfront what our columns, our attributes are going to be. So for our student table, we decide we need a roll number, a first name, a last name, and a department. This schema is now our fixed plan for exactly what kind of data is allowed in this table. And once we have that schema locked in, we can start filling it with our actual data. This collection of data at any given time is what we call the instance. And as you can see, each row, each tuple is one specific student, and all their information fits perfectly into the columns we defined. This is the living, breathing data that exists inside our structure. Now let's talk about those strict rules I mentioned, because this is where the magic happens. First, every single row has to be unique, no exceptions. You can't have two identical rows for the same student. It's just not allowed. Second, the order of the rows means absolutely nothing. And third, this one's important, every value must be atomic. That just means indivisible. You can't cram CS and EE into the department column. It has to be one single value. You know, these simple rules are the secret weapon against data chaos. So we've got our structure, we've got our rules, but how do we actually guarantee that every single row is unique? Well, that brings us to the most critical concept in this entire model. This is the magic ingredient that makes the whole thing work. Let's circle back to our original problem. We've got two students named Sanjay Sharma. If you just search for Sanjay Sharma, which one pops up? How do you make sure you're updating the right student's address or grades? We need a totally foolproof way to tell them apart. And the solution is the primary key. A primary key is a special column, or sometimes a few columns combined, where the value is absolutely guaranteed to be unique for every single row in that table. Think of it like a social security number or a fingerprint for your data. It's a perfect, one-of-a-kind identifier. So in our students table, the roll number is the absolute perfect choice for a primary key, right? Because even if we have 100 students named Sanjay Sharma, every single one of them will have a totally unique roll number. So the main takeaway is, if you know the roll number, you know with 100% certainty that you're looking at exactly one student. But you gotta be smart about choosing a primary key. Roll hunt is great. Every student gets one, and it's always unique. But what about something like a passport hunt? That's a terrible choice. And why? Well, because not every student is going to have a passport. That value could be missing. We call that null. And that makes it completely unreliable as an identifier. A primary key can never, ever be null. Okay, so we figured out how to uniquely identify every student in one table. That's great. But a real university is way more complex, right? They've got tables for courses, for enrollment, for grades. So how do we link all this related information together cleanly? And this is where the foreign key steps in. A foreign key is basically a column in one table that points back to the primary key in another table. You can see it here. The roll number in our enrollment table is a foreign key. It's not the primary key of this table, but it acts like a perfect bridge, linking every single enrollment record back to one unique student in our main students table. This is how we build this web of reliable connections across our entire database.
All right, so we've built this perfectly organized, beautifully interconnected set of tables. Now what? How do we actually get information out of it? How do we ask it questions?
You know, there are fundamentally two ways you can ask a computer to do something for you. The first way is procedural. That's where you give it a detailed, step-by-step recipe for how to find the answer. It's like finding a square root by giving it a complex algorithm of guessing and refining over and over. The other way is declarative. And here, you just describe what you want. You don't care about the steps. You just say, hey, find me the number that, when you square it, gives me n. And this is the absolute beauty of relational databases. They use declarative languages like SQL. You don't have to write some complicated program to find all the students in the computer science department. You just declare what you want, something like select first name, last name from students where department equals CS. You describe the what, and the database system is smart enough to figure out the how all by itself. So let's just pull this all together for a second. We've got tables with strict rules, we've got unique IDs called primary keys, and we've got these bridges called foreign keys. So why? Why have this simple structure been the bedrock of data management for over 50 years?
Well, the power is in the guarantees it gives you. You get consistency because all those rules prevent garbage data from ever getting into your system. You get accuracy because those primary keys make sure you are always looking at the right record. You get connectivity, which lets you build this rich, interconnected web of information. And you get simplicity because you can ask for exactly what you need without having to be some kind of master programmer.
And that really brings us to a final thought. This whole model was designed way back in the 1970s. That was long before the internet we know today, long before AI, and way before this explosion of what we call big data. And yet, it is still the foundation for countless critical systems we use every single day. So the real question for us is, in a world that's just awash with new, messy, unstructured kinds of data, how does this old idea of structure and order continue to hold up, and what's its place in our future?